We did the reflection principle for analytic functions. What was that? That we have a symmetric domain with respect to real axis. We have a domain symmetric. D has to be symmetric with respect to real axis, and then the upper half, that is the D plus itself, is a domain. And if we have an analytic function defined on this upper half, analytic, and when we say that it tends to 0, its imaginary part of f tends to 0 as z tends to any point on the real segment of this domain, then reflection principle says that in the reflected part of this domain, and what is the reflected part of this domain? And reflected part of this domain is this part. It says that then let it be d minus, then f extends to be analytic on whole of the domain D. That means we can extend it to be we can define it on this reflected part also, so that this function becomes analytic on whole of the domain D, and it also satisfies this identity that image of conjugate of Z is conjugate of image of Z. Okay, so now today and in the next lecture, we are going to generalize this reflection principle to some domains, and for that first we need to set certain terminology. We need to define first the analytic concept of an analytic curve, then free analytic curve, and then we will not most general part, but still more general than this reflection principle, where we consider only the domain which is symmetric with respect to real axis. And for that, the first, this kind of symmetry has to be extended, and for that we have first the concept of analytic curve. What do we mean by an analytic curve? Analytic curve is a curve, but it has some properties, and what are those properties we have to see. Suppose we have a curve, this certain curve gamma, and what it says that a curve gamma is said to be analytic curve, एनालिटिक कर्व या एनालिटिक आर्क भी बोलते हैं आप इसको. We might also call it analytic arc if for every point on gamma, for every point, let's take some point on this gamma, it says that for every point on gamma there is an open neighborhood, u of that point. For every point, let that point to be denoted as some, anyways, there is a neighborhood of the point, जो point हम consider कर रहे हैं, there is some neighborhood, and surely this is u, and there is a neighborhood of for which, इस neighborhood की कुछ property होनी चाहिए, for which there is a conformal map, let that map be notationally written as z zeta to z zeta of a disk T centered on the real line R onto U. See, you have to you have to have a disk whose center is let this be real line R, whose center is on the real line, such that image of the segment, this is D, and this image of this segment means the part of the real line in this disk D intersection R coincides with the part of the curve gamma in open neighborhood gamma, that is U intersection gamma. So what's it is? That means this gamma is a analytic arc. If for every point on this gamma we are able to find an open neighborhood, U is an open neighborhood of that point. It's open set, of course, and then we must have a conformal map from some disk D, and we must have this conformal map which maps zeta. Zeta is coming from here, the disk D, and it is mapped onto some point Z here, Z, and the important property which identifies it is that the image of this segment, real segment, should be or what you call it as the image of the part of the real line, image of the part of this real line should be this part of the gamma that lies in this open neighborhood. They must be same. Okay. Now this is the analytic arc. It must hold for every. It must be true for every point on this gamma. Then this gamma will be known as a analytic arc. Now let us observe certain more things, and for that let me. I don't want to retry any diagram. I will make space for everything that I have to talk here only. Okay. So let us, okay, suppose we have an analytic arc, gamma is an analytic arc. Definition is done. See now what other things that we are going to get. Suppose gamma is analytic arc, then by definition for every point on this gamma, we will have an open neighborhood of a point on that gamma, so that that neighborhood is conformally equivalent. When we say that we have a conformal map from disk onto this, that is equivalent to say that U is conformally equivalent to the disk T. Yeah, that's it. That means that this U is conformally equivalent to disk D, and this is a disk whose center is some real number. So what happens then? You know, this disk, when center is a real number, then this disk is symmetric with respect to real axis. You know, it is symmetric with respect to real axis. So if you have zeta here, then its conjugate will be lying. It will be its reflection through real axis, and then we have a map. If zeta is there, then we have a map from disk D to itself, which maps zeta to zeta conjugate. Okay, is a conjugate map. Is a conjugate map, but this is not only a conjugate. It's a you know, conjugate map is an anti-conformal map. What is a conformal map? Conformal map is where you have the angle and magnitude is preserved, but angle is preserved in sense. In direction of angle is preserved. Whereas in anti-conformal maps, magnitude is preserved, but angle is preserved only in magnitude, not in direction. The direction of angle is always reversed. So this conjugation is a anti-conformal map. This is anti-conformal self map of the disk D, because it is a symmetric disk. Z और Z conjugate इसी के अंदर lie करेंगे. So we have a function. We have this conformal map which maps zeta to Z zeta. So what we are going to see, अगर Z zeta का image Z zeta है तो zeta conjugate का image is also a some point. And see, we will see what is that point. So but first what we observe here, that this anti-conformal map induces induces uh, a map which maps Z to some Z star of this U onto itself. How it induces, and this is given by Z of zeta star is defined to be the image up under this conformal map of the zeta conjugate. So every this conjugate map defines this function, and we will see that क्योंकि आपके पास ये जो पार्ट है सेगमेंट का D intersection R, this is something which divides this disk into two parts. One is the upper half and another is the top half. You can say one is the top half, another is the bottom half of. ठीक है? And we have also this D intersection or segment is mapped onto this part of the gamma. This part of the gamma is what you can write it as, you may write it as U intersection gamma. And just let me change the color. And we have now this map, and we will see that actually whenever we have Z in the top half of this U, then its Z star will be in the bottom half. It cannot go on the top half. But first let us see what property this Z star has. We have this property is equal to Z. How you are going to see this? Look at this thing. Z star of zeta whole zeta. By definition, what is this thing? How do you define Z star? You define it to be Z of zeta conjugate whole star, and again how you will define it? It has to be Z of zeta conjugate whole conjugate. It is equal to Z of zeta. Hence, it proves that this is Z star. Double star means the conjugation of this map with itself, and this gives you the identity. And any function which when composed with itself, if that comes out to be identity, then such a function is known as an involution. So this function is involution. This function is a involution. Now, what does this conjugate map do? This conjugate map interchanges this top half of the disk. Let me choose some other color which I haven't taken, so that, yeah, red, blue already taken. Let's take this darker one. So this is the upper half. This is the top half of disk, and we have this bottom half of the disk. And this conjugation map, what it does is this conjugate map maps this top half onto the bottom half, and it fixes the real axis. Conjugate map क्या करता है? ये real axis को fix करता है, and ये real axis को fix करता है तो also we see that yeah, the real axis को fix करता है, then we say that Z star is equal to Z if and only if we have this Z of zeta conjugate is equal to Z of zeta, and we know that there is a conformal 1-1 map, means this holds only whenever zeta is equal to zeta star. And you know that when zeta equal to zeta star means that this holds whenever zeta is in the real segment, and under this conformal map, you know, this real segment is mapped onto the part of the arc, and hence this holds whenever zeta is in this part of the arc. That means this conformal map, this map only fixes this involution map. Let's call first for the time being to be an involution. This involution maps fixes only points which are on this part of the segment. Okay, and we will see that it doesn't fix any other point. And now how we are going to see, note further that note further that the map which maps zeta to zeta conjugate, the conjugation map, it interchanges the top half and the bottom half and the bottom half of this part t minus r, except the real axis, क्योंकि real part को वो fix करता है. तो which are the top half and bottom half are the two components of this disconnected part, which are the two components of this disconnected set t minus r, and hence the map z which goes to z star, it must interchange the two components of this u minus gamma, and you have this neighborhood gamma, and it let's take out this thing, let's take out this, then what is left to you is u minus gamma, and it will have two parts. One is this bottom half, another is this top one. And this conjugation map, what it will do, any point z, if z is here, oh okay, I just marked it. If z is here, its image z star will be in the lower half, and if it is in lower the half, its image will be in the upper half. And these two components are referred to as these two component. One is this upper one component, this is one component, this is component of u minus gamma. You have another component, this is another component of u minus gamma. Why it has two components? Because it's a disconnected part, we are taking out this gamma out of it. And these two components are known as sides of gamma, or neighborhoods of the sides of gamma. You may call them, you may call these two components to be neighborhoods of the sides of gamma. Is it clear?
Yes, sir.
And now finally, this map which takes z to z star is called the reflection across gamma. And we will see that whether this reflection is conformal and or it is anti-conformal. But you know that since the conjugation map is anti-conformal, it is anti-conformal, and we have this map which takes zeta to z zeta. By definition, this is conformal, This is conformal map, and so the composition which maps zeta to z of zeta conjugate is anticonformal. Composition of a conformal and a anticonformal map has to be anticonformal. That means the map which takes z to z star is anticonformal. It's anticonformal map. Okay, there's a reflection across certain part of section of the curve, and it's a anti-conformal map. And we will further have more properties of this, and the other property is that the reflection is unique. This reflection which takes z to z star in u is unique, but uniqueness has certain unique in the following sense. Unique in the following sense. What is the sense? That if there is an open neighborhood of a point in this part of the gamma in open neighborhood U, and an anticonformal map which takes z to, say we are giving this notation z plus, that fixes each point of gamma, because this reflection z takes to which takes z to z star is anticonformal also, and it fixes each point on this part of the gamma. And we suppose that we have such another function, we'll say it is z to z, z plus, and it fixes each point of gamma in the neighborhood then uniqueness will imply that z plus is equal to z star. See why it is unique. Let's try to verify. So suppose we have two such maps. One is the z taking to z going to z star, another is z going to z plus. Then their composition, note that the composition which takes z to z plus and then composing it z star, now it becomes a composition of two maps, and both the maps are anti-conformal, and composition of anti-conformal is a conformal map, and we know that this is conformal. This is a conformal, and hence analytic also. We're going to get this to be analytic map because it's always a continuously differentiable function, and there is a result when in general we have, whenever we have an analytic function, and if that analytic function is non-zero at certain points, then at those points the function is conformal. But for its converse, we have if we have a conformal map, and if it is continuously differentiable, and if it has its gradient is non-zero, and you will have all that properties here, and that will imply that the function is analytic. So we have this function analytic. I will state that result later on, but now this function becomes analytic, and now you see that it fixes each point of gamma, because z plus fixes each point of gamma, and z star also fixes, so the composition will also fix each point. And since this function z plus z star fixes each point on gamma, And when it fixes each point on gamma, that means this analytic function is identity function on this part of the gamma. Hence, by uniqueness principle, it follows that what it says that when uniqueness principle says that when you have whenever you have two analytic functions, and if those two analytic functions agree are equal uh, on a part of a set which has at least one non-isolated point, then the two functions are going to be same on whole of the domain wheresoever they are defined. Here we have these two analytic functions. One is obtained through composition of z plus and conjugate star, and this is equal to the identity function on the gamma, and gamma is a curve, and you know the curve is a connected region, is a connected it's a connected set, and it has no isolated points. Every point of it is non-isolated point, and we have two equality there on that part which has no isolated point. Hence, by uniqueness principle, these two functions are going to be identically equal on the part where they are defined. Now, let us see what happens next. So we have this composition to be identity. Now we have z plus, which I can write. You know that we have already seen that this star reflection is a involution. So z double star will be equal to this thing. And composition being an associative operation, we can write it as z plus z star. And as seen, this composition of this plus and star, this composition is identity. So this is equal to z star. And from here we see that these such reflections are unique whenever there is. So hence this proves that the uniqueness of this reflection. Is it okay? So what we did, we defined a reflection whenever we had this analytic arc. This is analytic. We are assuming this arc to be analytic, and we just pick up a point on this arc, and we chose certain neighborhood here, and then we saw that we can define a map from this u to itself. You can say that this is a map u to itself, and the map how you have defined to with z to z star, and how it is defined whenever z is in the top half, and its reflection through, that will be known as a reflection through the gamma, lies in the bottom half. Now this is a gamma, and a gamma is a compact set, because you know that gamma will be obviously defined is a continuous function, will be defined on interval, and we, without loss of generality, we may take that interval to be. So it is a, and you know that gamma is the trace of this function, and this open interval being a compact set implies that this is a compact. And what you can do now, you may choose finitely many points. I may choose another point here, and I can draw another open neighborhood here, somewhere here. Let it be u naught. I can similarly choose uh, another point here. I can draw another neighborhood here. Let it be u2 and u1. And in this way, finitely many neighborhoods, such neighborhoods will cover this entire gamma. Finitely many neighborhoods will cover this entire gamma. And around each neighborhood, you will be able to find this extension, this reflection z going to z star, z going to z star, z going to z star. And but by the time being, each reflection is specific to the open neighborhood that we are considering. Now the question is, can we extend this reflection? Can we define a function on a neighborhood of this gamma? What is the neighborhood of gamma? Gamma neighborhood का gamma क्या है? कोई भी एक open set जो इस पूरे gamma को contain कर रहा. So if you see के union of all these disks, union of all these disks. Let me take this union to be something whatsoever it is, j from 0 to some n. ये जो union है, this union, because gamma इसके अंदर है, you may see that gamma is contained in this, and each is an open set, so union is open set. So this is an open set containing gamma, hence is a neighborhood of gamma. Is a neighborhood of gamma. And now the question is, if we start from this u naught and we want to extend it to be, तो अब क्या होगा जब आपके पास दो नेबरहुड्स हैं, इन पर्टिकुलर लेट अस लुक एट, दो नेबरहुड्स हैं, क्या एक रिफ्लेक्शन एक नेबरहुड से दूसरे नेबरहुड पे एक्सटेंड होती है या नहीं है? फर्स्ट वी आर गोइंग टू सी दैट थिंग. I have to redraw again. We have one neighborhood here that shows other neighborhood here. We have a reflection, this is u, and let this be v, and we have z, this is z star. Okay, and एक और चीज हमें डिफाइन करनी पड़ेगी. तो क्योंकि v will be conformal equivalent to some disk, और वो डिस्क आपके पास क्या होगी? वो डिस्क आपके पास सेंटर रियल नंबर होगा उस डिस्क का. तो इसी तरह से u will also be equivalent to some disk. ठीक है, this will be something d naught and this will be something d1. आपके पास एक फंक्शन यहाँ से यहाँ होगा. ठीक है, तो ऑब्वियसली इनका इंटरसेक्शन ओवरलैपिंग पार्ट है, तो इन डिस्क्स का भी आपस में कुछ ओवरलैपिंग होना चाहिए जी. मैंने यहाँ सेपरेटली लिखा है, आई कैन नॉट राइट, आई नीड टू हैव डिस्क टू बी ओवरलैपिंग. ओहो, आई हैड यूज्ड इरेजर. Let me choose. Yeah, these are the two disks. So I have a function. By definition, analytic arc definition say we will have a function analytic from, let this function be some f. This will be from d1 to d2, and we will have another function from, this will also be what you say it is. Both these functions are conformal. F and g are conformal. Okay, and what happens then these two functions will agree here. We will be able to, I'm not going to get into much detail, but we will show that these two functions are same here, and this will imply at what you say, we may take the uniqueness principle will also come there, that these two, we have some w going to w star here, and these two reflections will be same through this thing. Okay, through this region, and then we have a reflection, new reflection, which is defined on the union of these v union u. We will be having a new function defined from v union u, and it will be another reflection. And how you will be defining it? You will be defining it to be z to z star s, and whenever z is in v, it will be go to its reflected point. Whenever it is in u, it will go to its reflected point. And whenever z is in the common region, in common region both the reflections are same. In this way, this whole reflection will be extended to whole of the neighborhood of this gamma. Okay, and then this completes that if you have an analytic arc, then you have a reflection in a certain neighborhood of that analytic arc. Okay, is it okay? So finally, what we require for our reflection principle is the idea of a free analytic boundary. Free analytic boundary arc. Boundary arc. What is a free analytic boundary arc? It says that let us take D be a domain and an arc gamma of the boundary of this domain is said to be free analytic arc, is said to be free analytic boundary arc if every point of gamma is contained in some disk U such that U minus gamma has two components. Whenever we take out that gamma from that U, then U minus gamma remaining portion must have two components. Components contained in D, one contained in D, one contained in D, and the other contained uh, in the complement of D. That would be better to say. Of D. You see, for example, let us take the circle just to see it. And let's not take the whole circle. Let's take the circle and let's take D to be the unit disk. This is D. And if we restrict to this part, and then what we can do, let this be the gamma. It's a part of this free analytic boundary arc. We are not taking the everything. We are not taking a whole of the boundary. We are just taking this part, and then I can draw a disk so that that disk contains entirely that part of the gamma. And you see, then if we take out the gamma, then it will have two parts. One, that green shaded region, the other will be this this one. These are the two parts of this U minus gamma, and one part lies entirely in domain in disk D, and the other part lies outside D. Let's look at a certain non-trivial example. There is a you need to get into it. Suppose we have a domain D, and how we are going to domain D? D is obtained from half disk Z mod Z less than 2, not half disk, it's the disk, by excising a sequence of disjoint closed disks from the top half accumulating on the interval -1 and 1. What you are doing, you have a disk, and इसका जो -1 और 1 interval होगा वो यहाँ होगा, ठीक है? This will be some interval. So what you are going to do, you are just punching out some disks, closed disk, disjoint closed disk, ताकि उनकी boundaries भी एक दूसरे से मैच करें, ठीक है? A sequence of such closed disks you are punching out. You might take much smaller than Okay, then you might take further smaller discs. So इस तरह से you are punching out these discs from this upper half of this. Then ये सारा पंच आउट करके जो आपके पास डी पीछे बचता है, तो उस डी की जो बाउंड्री है वी विल सी के वो, अब ये जो बाउंड्री सर्कल्स है, ये जो छोटी छोटी डिस्क्स को हम बाहर निकाल रहे हैं, वी आर टेकिंग आउट दोज डिस्क्स, तो वो जो पीछे इन डिस्क से जो सर्कल हैं वो इसके बाउंड्री आर्क्स हैं। तो जैसे पहले रेड सर्कल को देखिएगा, ये बाउंड्री आर्क है। तो ये बाउंड्री आर्क क्या है? ये बाउंड्री आर्क आपके पास फ्री एनालिटिक बाउंड्री आर्क है, क्योंकि इस बाउंड्री पे आप कोई भी पॉइंट लें, उस पे कोई डिस्क ड्रा करें, तो उसका you will always have a disk. Let me choose some color. Which color I should take? Yeah, यहाँ पर in particular आप कोई भी चेक करिए, you might always be able to draw a disk. तो उस डिस्क का एक हाफ आपके पास इस होल में चला जाएगा, which is a not part of the domain D, and another part will be in this. तो इस तरह से हर एक में, इवन के आपके पास जो जो भी डिस्क है, you will be able to draw. बट आपके पास यू आर टेकिंग द डिस्क की जो सीक्वेंस है, वी आर टेकिंग स्मॉलर डिस्क, तो उस तरह से आपके पास जो ये -1 to 1 आपके पास इंटरवल आता है, तो ये -1 to 1 वाला जो आर्क है, ये फ्री एनालिटिक नहीं है। क्यों? क्योंकि आपके पास whenever you will take a disk at certain point here on this interval 0 1 -1 and 1, when you are any disk, तो आप क्या ले रहे हैं? आप ये जो सीक्वेंस ऑफ क्लोज डिस्क ले रहे हो, तो ये एकोमुलेट हो रही है। तो whenever you will have जो ये एक पार्ट है, इस पार्ट में इस रीजन में you will have certain part of the disk जो एक्सपंज किया गया होगा, जो पंच आउट किया गया होगा वहां से। तो उस तरह से ये वाला पार्ट जो अपर हाफ वाला पार्ट होगा इस डिस्क का, उसका कुछ पोर्शन डी में रह रहा होगा और कुछ पोर्शन डी से बाहर। लेकिन फ्री एनालिटिक बाउंड्री के लिए आपके एग्जैक्टली वो हाफ या तो बाउंड्री के बाहर या डोमेन के बाहर होना चाहिए या डोमेन में होना चाहिए। तो दिस इज अ काइंड ऑफ नॉन ट्रिवियल एग्जांपल टू कंस्ट्रक्ट फ्री एनालिटिक बाउंड्री। एनी क्वेश्चंस? No, sir. So finally, I will stop here with this, giving you an example. I have a map z zeta equal to zeta minus I, and this is zeta plus I. You see that this is a bilinear transformation, and see it will send, I'm just writing in brief, it will send your extended real line to unit circle, and you will see that it will be an analytic unit circle will be, and you can then from this you can see that this unit circle is a what is say analytic arc, and analytic arc है, तो फिर इसका रिफ्लेक्शन देखिएगा थ्रू सर्कल क्या है। ठीक है, तो इसका रिफ्लेक्शन बाय डेफिनेशन होना चाहिए z स्टार हैज टू बी, आप जीटा का कंजुगेशन करते हैं जीटा माइनस आई अपॉन zeta conjugate plus I, and this can be written as zeta minus I whole conjugate plus whole conjugate upon zeta minus I whole conjugate. You may write it as zeta plus I upon zeta minus I whole conjugate. And what is this zeta plus I upon zeta minus I? This is the reciprocal of this z. ठीक है, तो ये बन जाता है 1 upon z का होल कंजुगेट बन जाता है। तो 1 upon z कंजुगेट को आप लिख सकते हैं when you multiply it with z or divide by z, you will get z upon z into z conjugate will be mod z square. ठीक है, from here you can just discuss its geometry. You have to discuss के जब सर्कल के अंदर रिफ्लेक्शन होगी, सर्कल के अंदर किसी भी पॉइंट की रिफ्लेक्शन होगी, तो वो कहाँ पे होगी। ठीक है, थ्रू दिस। तो जस्ट ट्राई टू सी इट, इसकी इमेजेस देखिएगा हाउ टू डू दिस थिंग, एंड वी विल स्टेट शिवाज रिफ्लेक्शन प्रिंसिपल इन